Hello everyone, welcome back to the channel uLearn Education Online.
Here we have seen some of the DC characteristic parameters, that is input bias current and what is input bias current and how it is compensated, and the second parameter is input offset voltage and what is it compensation method. Now in this video you are going to see the other three parameters, that is the input offset current, what is input offset current and how it is compensated, and the fourth one is the thermal drift. Last the we are going to see is output offset voltage. Now first we are going to see what is input offset current. So as we know that the bias current or the offset current that is present in the op amp is caused because of bias currents present at the input terminals of operational amplifier. Now what are the input terminals? One is the inverting terminal and the other one is the non-inverting terminal. We are indicating with as IB. Okay, so in ideal case we are considering that these two currents are equal, that is IB minus equal to IB plus, whereas in practical these two currents are not equal because of some parameters that is present in internal of op amp. Similarly we can say that because of an offset null or from the power supply or due to the mismatch parameters in the transistors that are considered during designing, out of all these parameters in practically we can say that these two bias currents are not equal. So in order to nullify this current, we have used one compensation technique, that is the usage of or compensation resistor at the input of non-inverting terminal. That is one method. Now we can see that the other definition, that is the offset current. Here this offset current is nothing but the amount of the difference between the IB minus and IB plus currents. We can consider it as an input offset current and it is indicated by I suffix iOS. So similarly it is defined as the algebraic difference of bias currents at the input terminals of op amp. So mathematically we can write the equation as iOS is magnitude, means since we know that the current is always a positive, so difference of non-inverting terminal current minus inverting terminal current. Now we are going to see how we are using a compensation in order to nullify this I suffix iOS value. Now simply by using a bias current compensation technique and with the modification of some parameters, we can get the nullified output voltage 0 even if the input signal is not present. Okay, now simply examine this the current flowing through these input terminals with the adding of or compensation resistor. So we know that this circuit is nothing but the input bias current compensation circuit, and here the input signal is applied at the inverting terminal of op amp. So even providing the compensation resistor at the non-inverting terminal, we are not getting the V0 value as 0 even if the Vi value is 0. So in order to provide a solution, we are finding what is the output voltage V0 in terms of input offset current, and how we are going to nullify that input offset current we are going to see now. We are performing the same analysis exactly what we did in input bias current. The same analysis is repeated. So here in the input bias current we are finding the output voltage V0. So V0 we can write the expression as, by applying simply KVL, it is V0 is equal to I2 into RF minus V1. So in this equation, what is the unknown parameter? One is unknown value is I2 and other one is the unknown value V1. So we know that this V1 is nothing but the voltage drop across the R compensation resistor. So here we, from the Ohm's law, we can write V is equal to I into R. Now what is the current flowing through this R compensation resistor? It is nothing but the IB plus. So we can write the V1 as IB plus into R compensation. So from this equation we know what is the value of V1. Now the other one we don't know is the value of I2. Now how we are going to find out the value of I2 in terms of bias current compensation is by simply applying a node analysis, or by simply applying a KCL at this node A. So if you observe at this node A, what are the entering currents? The entering currents are I1 and I2, whereas the leaving current is IB minus. So we can write finally the nodal and the KCL equation at this node is entry currents are I1, I2. So we can write minus I1 minus I2 plus IB minus equal to 0. So from this equation we get the value of I2 as IB minus minus I1. Now what is the value of I1? So here the I1 is nothing but the current flowing through the resistor R1. If you simply write the current equation, it is VI minus of minus V1 by R1. So here VI is 0. So finally we can write the I1 as V1 by R1, and we know what is the value of V1. It is IB plus into R compensation. So finally the I1 is IB plus into R compensation by R1. Simply substitute the value of V1 and I1 in this V0 expression. So finally we'll get the V0 as IB minus minus of IB plus into R compensation by R1 into RF minus V1 is IB plus into R compensation. So if you simplify this equation, so V0 value will get as RF into I suffix IIOS. So here IIOS is nothing but the difference of IB minus and IB plus. So for a typical IC741, for example, if we consider, we know that the RF value is 1 mega ohm and the input offset current value is 20 nanoamperes. So finally the output voltage V0 value numerically we can obtain as 1 mega, it is 10 power 6 into 20 nano means it is 20 into 10 power 9 minus 9. So finally the V0 value is 20 millivolts, so which is very less. But if you consider the low power applications, this millivolt will create a severe problem in designing of applications. So in order to compensate that millivolt signal also, we are simply modifying this circuit. That is, so here this nothing current is nothing but flowing through the resistor RF. So if you minimize this current, offset current, then finally we will obtain a zero output voltage signal at this op amp. Okay, so now how we are reducing this IIOS is by simply modifying this resistor, or we can say that by adding a network to this resistor. So in place of this RF, we are simply adding a T network, T shaped network, which consists of resistors. Okay, so this is, we can say, it is also called a star network. Okay, so RF value is modified with this star network, which is RT and RS. So in this is the procedure how to reduce the output voltage V0 0 even if there is a small amount of current present at the input terminals of op amp. So this is how we are producing a compensate, or we are providing a compensation to the input offset current. So in the input offset current, one thing we are going to see is the modification of change in the circuit of input bias current compensation. Okay, till now we have seen the three parameters. One is input offset voltage, input bias current, and input offset current. So now we are going to see the fourth parameter, that is thermal drift. So this thermal drift will occur if the three parameters will change if there is a change in environmental conditions. So what is the environmental conditions? The main condition, that is the temperature. Even if there is a change in temperature, how the circuit will react. And the second one is if there is a fluctuation in the power supply. Okay, now we are going to see how the transistor characteristic parameters will change if there is a change in temperature. Okay, so if you consider, that is IB, nothing but a bias current. So if the temperature is goes on increasing, this IB value will exponentially decreasing. So we can say that the input bias current drift, we can write it in terms of delta IB by delta T. So here delta IB indicates the difference of bias current if there is a change in temperature, and it is measured in nanoamperes per degree centigrade. And the second drift we are going to see is input offset voltage. Okay, so input offset voltage VIOS. So here if there is a change in temperature, then this input offset voltage is exponentially increasing, so we can say it as input offset voltage drift. And the third parameter is input offset current. So this input offset current is also exponentially increasing. So these are the graphs how it will increase its value if there is a rise in temperature or there is a low in temperature. And the last parameter is output offset voltage. So this output offset voltage definition is a minute amount of output voltage present at the output node of op amp even if the input terminals are grounded. So simply it is indicated with V suffix OOS. So here the mathematical expression of the output offset voltage is VOT is 1 plus RF by R1 into VIOS plus RF into IB. And if a OR compensation is used in the circuit, then it is indicated with IB is replaced with IIOS. Okay, simply these are the formulas. Thank you.